Okay, so this is the last week of linear algebra. Okay, so in this week, I will talk about eigenvalues and eigenvectors. Okay, fine. Okay, so in eigenvalue and eigenvector, we usually solve this kind of problem. Okay, so first I will ask, what is the meaning? What is the meaning of? Can someone tell me what does it mean by A into X, where A is a matrix and X is a vector? Tell me. Okay, so you are not speaking, so let's forward. So suppose A, I'm talking about just a arbitrary matrix. Suppose I have A equal to 2 0 0 minus 2 matrix, okay, and let's take X as a vector 1 and minus 1. Now find A into X. So which means that you will get this thing, right? So you can see that this matrix is acting on this vector and it results in another vector. So you can see that we can also write it in this form. A into X, okay? So geometrically, if I plot this kind of operation, then you will see that suppose it's the x-axis and y-axis. Now it is saying I have a vector 2 0. I have a vector 2 0, that is nothing but this x equal to 2 and y equal to 0. Now it is multiplied by scalar 1, which means that it will be directing towards this direction, and this vector is nothing but 2 comma 0. Now if you look at this vector 0 comma 2, so which means that 0 and minus 2. So this is the vector 0 comma minus 2. Now it is being scaled by minus 1 times, which means that magnitude will remain same. It will just change its direction. So this is the vector. This is the vector what? If you multiply with minus 1, then this will become 0 comma minus 2. Now after adding this, you will get a resultant vector, right? So what is this vector? This vector is nothing but 2 comma 2. Now I will see the initial vector. So what is the initial vector? 1 comma minus 1. So 1 comma minus 1. This is the initial vector. So you can see that the initial vector was this and the final vector becomes this, which means that this matrix is nothing but a kind of transformation matrix. It is a kind of linear transformation. Linear transformation. So you can see that after the linear transformation of this vector that is OA, it becomes OB, which means that there are kind of two operations. One operation is what? Rotation, plus second operation is called what? Scaling. Okay, so which means that this AX matrix is nothing but a kind of transformation of this vector 1 comma minus 1, and it results rotation plus scaling. Now I will move to this case, Ax equal to lambda x. You can see that what I want is, if I have a matrix A, now I will act this matrix on X such that the resulting vector, I mean the OB vector, is such that it will be exactly in the direction of X by scaling lambda, which means that suppose you have a vector X. Okay, now after acting this matrix A on X, it will result the same direction, that is X, but it will be either this direction is scaled or this direction scaled. So which means that if it is a matrix, if it is a vector, initial vector is X, then what it will become X dash, and X dash is nothing but lambda times X. So this is the complete game of eigenvalue and eigenvector. Now the thing is, I have to find such vector such that the matrix A acts on X and it will give the same direction as X, but it will be scaled by lambda. So such vector X will be called as eigenvector. Since it will be family, that's why I will write eigenvectors. And there will be some chances that there will be many chances that you will get many eigenvalues. So that's why it will be called lambda will be called as eigenvalues. It's fine? Tell me. It's fine or not? Are you getting it?
Yes, sir.
Okay, I will give you the reference about this.
Hello, sir.
Yeah.
Can you let me in, sir? I am entering from desktop laptop.
Okay, but I think I have automatically. I have added as a automatically, so everyone will be. Okay, let me join.
Now it's working, sir.
Yeah, let me join from my phone so that I can admit all.
Sir, there is some problem.
Yeah.
We could not get into the meeting from the other device.
Wait, just a minute. Just a minute. Yeah, tell me. What you are saying? Tell me.
Actually, I could not join from the other device.
Okay, try to join it again. I will add.
Okay.
Okay, so I will give this kind of transformation or every kind of game in linear algebra. You can see by the animation, there is a YouTube channel called 3 Blue and 1 Brown. Have you heard about it? YouTube channel. Okay. Let's take an example. Fine? Is everything fine now? Should I move?
Sir, this has been discussed today, this linear transformation.
This actually, I can discuss it, but the thing is, this is not in your syllabus, so I will not. But yeah, I mean,
No.
I can give one YouTube video. I will upload it if you want. But in your case, I mean, in your syllabus, I will not discuss it. Linear
Sir, what
transforms.
about the YouTube channel you are talking?
Okay, at the last of the lecture, I will give you the link. Okay.
Okay.
Okay. Till now it is fine, right?
I haven't missed anything.
No, we have nothing. I don't think that you have missed something. I will. I mean, I will suggest you to please join on time. Okay. Otherwise, definitely you will miss it.
I was not getting into the meeting.
Okay. Okay. I will revise it again. Okay. At the end of the lecture. Okay. Fine.
Thank you, sir.
Yeah. Now I'll take an example. Suppose if A is a matrix 3 0 8 comma minus 1. Okay, and I have a vector 1 2. Now I want to find eigenvalue. So what will I do is I will find AX. So that is nothing but 3 0 8 minus 1 1 2. Since I have already given eigenvector, which means that I have to just find eigenvalue. Okay, so you will get it 3 6, and you can see that it is nothing but 2 times, not 2 times, 3 times, 3 times of 1 2. So what is the eigenvalue? You can see that that is nothing but Ax equal to 2 times lambda, so 2 times x. So which means that lambda equal to what? Not 2 3.
3.
Yes. So lambda equal to 3. So in this case it is eigenvalue is what? Lambda equal to 3. So but the thing is here I have already given eigenvector. In many cases, in general, you will be given only matrix. Suppose I have a given matrix A, and you have to find eigenvalue and eigenvector. So what will you do? So the question is, I have written identity matrix, which means that it will not affect on x. Okay, so the question is, what are x and lambda? So this is the question. So what will I do is I will just move from the right hand side direction to the left hand side direction, and I will equate to the 0. So you can see that that is nothing but a minus lambda I times x equal to 0. Now you can see that this is a kind of homogeneous equation, right? Homogeneous,
Yes.
yes, homogeneous linear system of equation. Now I want what? Non-trivial solution. So if I want non-trivial solution, then what does it mean? Determinant of a minus lambda I should be what? 0. Okay, so what is the determinant of a minus lambda I? So determinant of a minus lambda I means, if suppose a has an element a11, a12, something like that, a21, a22, a31, a33, 32, dot dot dot, and it should be n by n matrix, right? Because for the determinant, matrix should be square. Okay, so this minus lambda times identity matrix. Should be equal to 0. So what is the determinant? So you can see that after multiplying lambda with this identity matrix, the lambda will move to the diagonal. that is equal to 0. Now, if you simplify this, you will get a polynomial. If you simplify this, you will get a polynomial of n degree. And what is that polynomial? That polynomial will be of the form of lambda minus lambda raised to the power n plus c1 lambda n minus 1 minus c2 lambda n minus 2 plus there will be alternate, okay, and finally there will be cn equal to 0. So when you determine the determinant of this matrix, you will get a kind of polynomial of n degree. Now the question is, what are c1, c2, c3 like that? So c1 is nothing but lambda 1, lambda 2, lambda 3. This n polynomial will have what? N roots. Okay, and what are those roots? Roots are lambda 1, lambda 2, dot 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 lambda n. Now I'm saying that c1 will be lambda 1, lambda 2, lambda 3, dot dot dot. What is c2? c2 is nothing but lambda 1, lambda 2 plus lambda 2, lambda 3 plus dot 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 dot. What is c3? c3 is 3 times. Here you can see that I'm multiplying one with 1 by 1, and c2 is being multiplied by 2 by 2. Similarly, c3 is lambda 1, lambda 2, lambda 3. Okay, that will be lambda 1, lambda 2, lambda 4. That will be lambda 1, lambda 2, lambda 5. I mean 3 times. What will be those combination? You have to take 3 times. Similarly, Cn will be what? Tell me. Cn will be what? If C1 is this, C2 is this, C3 is this, what will be the Cn? Tell me.
N times combination of lambda.
Yes, lambda 1, lambda 2, lambda 3, lambda 4, dot 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 lambda n. So this is the thing. Okay, and although these coefficients are called invariants. What is called? Invariants. And why it is called invariants? Do you have any idea? What does it mean by invariants? Tell me. Invariants means whatever you will do, any kind of rotational transformation of this matrix, that matrix A, whatever you do, any kind of rotational transformation of A, the coefficient will remain same, which means that these invariants will remain same. It's fine, which means that suppose you have a matrix A, okay, now you are doing some kind of transformation like that, Q A Q transpose, you will get another matrix. Now find C1. C1 is what? Lambda 1 plus lambda 2 plus lambda 3. Similarly, when you find C1 of this A dash, you will get same thing. Similarly, when you find C2, here C2, these invariants will not change. That's why it is called invariants. When you do any kind of coordinate transformation means what? Not translational, only rotational. Okay, rotational transformation. Your invariant will remain same. Fine. Now this polynomial is also called characteristic equation. Okay, let's take an example. Okay, I will also talk about the very familiar case. Suppose if you have a matrix 3 by 3 matrix A11, A12, A13, okay, A21, A22, A23, A31, A32 and A33, okay. So for this, what will be the characteristic polynomial? You will write minus lambda q plus c1 lambda square minus, you have to take care about that, there is a alternate plus minus plus minus plus minus, so minus c2 lambda plus c3 equal to 0. Now here some people, I mean in many textbook, people usually write c1 as I1 lambda square minus c2 as I2 lambda plus c3 as I3 equal to 0. And here I1 is called lambda 1 plus lambda 2 plus lambda 3, that is trace of matrix A. And I2 will be lambda 1 lambda 2 plus lambda 2 lambda 3 plus lambda 3 lambda 1. And if you want to write in terms of trace of A, that is called, that you can write 1 by 2, that you can write 1 by 2 trace of A of whole square minus trace of A raised to the power 2. After solving, you will get the same thing, okay. Now I3 is nothing but lambda 1 lambda 2 lambda 3. This is what? This is determinant of A. For 3 by 3 matrix, these three are invariants. So you can see that whatever you do, any kind of transformation, trace of the matrix will remain same. A trace of A square will be also remain same, and determinant of A will also remain same. So that is the idea. Are you getting it? Tell me.
Sir, these conditions that we have derived, are they the same for the eigenvalues that we use to solve the questions, like the relations?
Yes, these lambda 1, lambda 2, lambda 3 are not nothing but the eigenvalues. Okay, let's take an example. Suppose I have a matrix 0, 1, 0, 0, 0, 1, 4, minus 17, 8, right? Now I have to find x and lambdas, okay. So what is the characteristic equation? That is A minus lambda I equal to 0, okay, fine. Now, so what will be the determinant? Determinant will be, you can write 0 minus lambda, 1, 0, 0, 0 minus lambda, 1, 4 minus 17, 8 minus lambda, that will be equal to 0. After solving this, you will get a polynomial minus lambda cube minus 8 lambda square plus 17 lambda minus 4 equal to 0, okay. And after solving this cubic, you will have a factor lambda minus 4 and lambda minus 2 plus square root of 3 and lambda minus 2 minus square root of 3 equal to 0. So the roots are lambda equal to 4, I mean lambda 1 equal to 4, lambda 2 equal to 2 plus root 3, lambda 3 equal to 2 minus root 3. So these three are eigenvalues. Now I want to check it. Suppose I want to find I1. I1 will be what? Sum of these lambdas. So you can see that 3 root 3 will be cancelled out and you will get 4 plus 2 plus 2, which means that what? 8. Okay, and that is nothing but the trace of A. Now find the trace of A. You can see that 0 plus 0 plus 8, that is nothing but the 8. Okay, now I want to find I2. I2 is what? Lambda 1 lambda 2 lambda 2 lambda 3 plus lambda 3 lambda 1. And after solving it, you will get what? Just tell me, what will you get?
A determinant of given matrix.
No, I3 is the determinant. What will you get? Just identify from this equation. What will you get? I just talked about that, right? Always characteristic equation of 3 by 3 matrix will be in this form. You can see that this minus I2, that is the lambda 1 lambda 2 plus lambda 2 lambda 3 lambda 3 lambda 1, which means that it is already given plus, which means that that should be minus 17. And find it, you will get the same. After putting these 3 lambdas in this equation, you will get minus 17. And determinant is what? Just multiplication of this. 4 times what? 2 plus root 3, 2 minus root 3, that is nothing but 4 minus 3. 4 times 1, 4. Now find the determinant. Determinant. What is the determinant of A? You can see that I have to just take this element, that is minus 1 times, exclude rows and columns, you will get what? 0 minus 4, that is 4. That is the answer. So this is the thing. Now this is all about the eigenvalues. Now I will move further regarding the eigenvectors. Okay, so before moving that, I will first introduce a theorem. If A is an n by n matrix, n by n triangular matrix, not just matrix, triangular matrix. Triangular matrix. And what are those? Upper, lower, and diagonal matrix. Okay, then eigenvalues of A are what? Are the entries on the main diagonal matrix, main diagonal of A. What does it mean? Which means that suppose you have an upper triangular matrix, something like this: 1 2 3 0 5 7 0 0 9. So it is saying that if you have such triangular matrix, that is upper triangular matrix, lower triangular matrix, or diagonal matrix, then eigenvalues of A are nothing but these diagonal elements, which means that lambda 1 equal to 1, lambda 2 equal to 5, and lambda 3 will be 9. Okay, so you don't have to solve that characteristic equation, you will get the same result. Okay, is there any problem here?
No, sir.
Okay, now let's move to the eigenvectors and eigenspace. Both are same, okay, don't confuse with this. So who is this using it? A. I think someone has put the cursor on that one note. Please remove that if you are using it. Why it is okay? This is my issue. Okay, just wait a minute. I will just cut it. Okay, I will use it again. Okay, so in eigenvector, I have to solve which equation? This. Ax equal to lambda x, and that can also be written as Ax equal to lambda I x. Okay. So you can see that I can also write it as a minus lambda I into x equal to 0. It is nothing but solution of which matrix? Homogeneous system of A minus lambda I matrix. So you can see that whatever I've already talked about the null space, right? Can someone tell me what is the null space? Can you recall it? Null space. I've already talked about, right? So the null space means when you solve Ax equal to 0. So whatever that solution space is called what? Null space. So here A is different. Here A is A minus lambda I. So which means that eigenvector or eigenspace are what? Null space of A minus lambda I matrix. Okay, is there any problem here? Let's take an example. I have a matrix A equal to 0, 0, minus 2, 1, 2, 1, 1, 0, 3. Okay. So what is the characteristic equation? Characteristic equation will be determinant of A minus lambda I equal to 0. So I have to write 0 minus lambda, 0 minus 2, 1, 2 minus lambda, 1, 1, 0, 3 minus lambda equal to 0. So after finding the determinant of it, you will get minus lambda, 2 minus lambda, 3 minus lambda. Fine? And minus 2 minus times of 2 minus lambda equal to 0. You can see that 2 minus lambda is a common, and that is minus lambda, 3 minus lambda plus 2 equal to 0. So you will get 2 minus lambda and another 2 minus lambda, and the different one is what? Lambda minus 1 equal to 0. So which means that you have lambda equal to 1 and lambda 1 equal to 1, and lambda 2 comma lambda 3 both are same, that is nothing but equal to 2. Okay, so these are the eigenvalues. Now I want to find eigenvectors. So what will I do? For lambda equal to 2, that is nothing but lambda 2 comma 3. So I will just plug in this lambda in that. So Ax equal to 2 times I x. Okay, so that matrix will be what? A minus 2i. A minus 2i times x equal to 0. Now plug in. So here, so 0 minus 2, 0 minus 2, 0 minus 2, 1, 2 minus 0, 2 minus 2, 1, and 1, 0, 3 minus 2, 1, 0, 3 minus 2, and x1, x2, x3 equal to 0, 0, 0. Here at the place of x, I have assumed what? x1, x2 and x3. So -2, 0, -2, 1, 0, 1, 1, 0, 1. This will be x1, x2 and x3, 0, 0, 0. Okay. Now use the elementary row operation. You can see that these two rows we can eliminate it. Okay. And after dividing the first row by -2, you will get 1, 0, 1. And after subtracting these two rows, you will get 1, 0, 1, 0, 0, 0. Okay. And in the next step, I will also subtract these two. Here in this step, what did I do? R1 minus 1 by 2 R1, and also R3 change to R3 minus R2. And here in the next step, I will do what? R2 change to R2 minus R1. So I will get 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, x1, x2, x3 equal to 0, 0, 0. Now you can see that these two rows are completely 0. So I have only one equation, that is x1 plus x3 equal to 0. Now can you tell me how many pivots are here? One pivot, right? And how many free variables? Two free variables. Okay, fine, good. So at the place of free variables, and which variable are free variables? x2 and x3, right? So let x2 equal to t and x3 equal to s. Okay, so what will I get? x1 equal to what? Minus x3, that is nothing but minus s. Now arrange it. So the first eigenvector is x1, x2, x3, and we can write it as x1 is what? Minus s, x2 is what? T, and x3 equal to what? S. Okay. Now I can write it as a two scalars, s and t. And when you write it, you can see that it has a coefficient -1. It has s coefficient 0. It has s coefficient 1. And at the place of t, it has 0 coefficient. So 0, 1 and 0. So V1 is what? Is a set of these eigenvectors. You have to keep this in your mind. For every corresponding eigenvalues, you will have many eigenvectors. People usually get confused because that they think that if I get one eigenvector, which means that corresponding eigenvalue, I will have only one eigenvectors. But it is not correct. For corresponding eigenvalue, you will have many, infinite number of eigenvectors. Because you can see that it is a scalar multiple of s and t. Whatever you will put s and t, you will get v1. So which means that the vector v1 is nothing but what? Spanning by these two vectors. It's fine. So this is the eigenspace. This is the eigenspace corresponding to this eigenvalue, lambda 2, 3 equal to 2. Okay, this eigenspace is what? Eigenspace of lambda 2, 3 equal to 2. Now I have another eigenvalue, that is lambda 1 equal to 1, right? That was lambda 1 equal to 1, okay? Yes. Now again do the same thing. You will get -1, 0, same thing, right? A minus lambda I x. This time I will assume it y equal to 0. So you will get 1 0 minus 2 1 1 1 1 0 2. Am I right or not? y1 y2 and y3 equal to 0 matrix, 0 vector you can say. Now I will do the same row operations, elementary row operation, and after doing this you will get 1 0 2 0 1 minus 1 0 0 0, and that is y1 y2 y3 0 0 0. Now tell me how many number of pivots are here?
2,
2. Free variables?
1.
1. Fine. So which means that if I have only one free variables, which means that this eigenvector will have only one, that is scalar multiple. Let's see how. So the first equation is what? y1 plus 2y3 equal to 0. And second equation is what? y2 minus y3 equal to 0. So you can see that if you take this as a y1, y2, y3, then for this variable you can take it as a free variable. So let's take y3. Let's take y3 equal to what? T. So what will you get? y2 equal to t. And what is y1? That is nothing but 2y3, and that is minus 2t. So just arrange it. That is the second. You can take it as v3. So y1, y2, y3, and that is minus 2t. y2 is what? T. y3 is equal to what? T. So just take t as a common, minus 2 1 1. So this is the corresponding eigenspace. Eigenspace corresponding to eigenvalue lambda 1 equal to what? 1. Okay, so this is the way to find eigenvalues and eigenvectors. So v3 you can also write it as fine. Tell me, is there any problem here?
No, sir.
Yeah. Now let's move to the another thing, power of the matrix. Power of matrix. Using the concept of eigenvalue eigenvector, you can also determine a raised to the power n kind of matrix. Suppose you have a matrix A, and if you want someone who wants to determine what is the A raised to the power 100, then it will be very difficult. But when you use the concept of eigenvalue and eigenvector, you can easily determine. How? Let's see. Suppose I have an equation ax equal to lambda x. Okay. Now multiply both sides by again matrix A. So you can see that this is a scalar, right? So we can take it as outside and you can write it as this. Okay. Now you can see that this is what? A square x equal to lambda times, and again at the place of ax you can write lambda time x. Okay. So that will be a square x equal to lambda square x. So what does it mean? Which means that, and similarly you can do nth operation. So you will get it a n x equal to lambda to the power nx. So you can write if x and lambda are eigenvector and eigenvalues of A, then first, what is the eigenvalue of A raised to the power n? Hmm? If the eigenvalue of matrix A is lambda, then what is the eigenvalue of A raised to the power n?
Lambda raised to power n.
Lambda raised to the power n. Similarly, what is the eigenvector of A raised to the power n? Tell me. It will be x only.
X only.
Yes. So you can see that that is the power. That is the power of the matrix. So you can see that if you have a matrix A, okay, and someone wants to find what is the eigenvalue of A raised to the power 100, so you have to just tell them that lambda raised to the power n, but eigenvector will be same. Fine?
So,
Yeah.
if we consider a vector and take lambda as a scalar, then the eigenvector is just the magnification of that. Lambda is just the magnification of that vector.
Yes, you are getting just now because I have already talked about that very first few minutes and also talked about the geometric interpretation of that. You missed that.
Yes.
Okay, let's just give 1 minute for you. So suppose, what does it mean by A into X? A into X is nothing but the linear transformation of matrix A on the vector X. Suppose you have a vector 1 comma minus 1. So you can see that after the multiplication of this matrix on A, you will get 2 2. Now you split this matrix in this vector form. Can I write it like this? Tell me. This, yes. So you can see that this operation, I mean the linear transformation by the matrix on this vector is nothing but this kind of operation. Now take the geometric interpretation. You can see that this line is a vector 2 comma 0 and it will be scaled by 1, which means that it will remain at the same direction. Now take the vector 0 comma minus 2. This is the vector 0 comma minus 2. Now it will be scaled by minus 1 times, which means that magnitude will remain same but direction will be reversed. So this is the vector OB. Sorry, this is the vector. Now the linear combination of these two are nothing but the vector OB by the use of parallelogram law. So you can see that earlier, what was the earlier vector? Earlier vector was 1 comma minus 1. That was nothing but this vector. And after linear transformation, this vector has transformed to vector OB. What does it mean? Which means that operation AX is nothing but the linear transformation. Linear transformation by matrix A on the vector. So you can see that this vector has transformed into this vector, which means that it has been rotated and also it has been scaled. So this kind of linear transformation has been done. Now I will talk about this thing. You can see that the linear transformation A on X, and I want to get such kind of operation such that I will get the same X but it will be scaled by lambda, which means that earlier if I have a vector OX, then I need some kind of linear transformation such that the direction will remain same but it will just scaled by lambda times. So that linear transformation is called what? Eigenvalue and eigenvector game. So which means that the scaling is called what? Eigenvalue, and those X is called what? Eigenvectors. It's fine now?
Yes, the lambda is the amount by which we scale the vector x
Yes.
in the same dimension.
Yes, which means that this matrix A, the transformation of the matrix A on X is nothing but just scaling, not rotating. it has just scaled the vector. And that is a very beautiful application in solid mechanics when you study stress tensor. Okay?
Yes.
Yes. Okay, so let's move further. Now, I have another problem. Suppose if A has a matrix minus 2, 2, 3, minus 2, 3, 2, minus 4, 2, 5. Okay? First problem is find eigenvalues and eigenvectors of A. Okay, and second problem is same thing but of A inverse, and third same thing but of A plus 2I. Can you find it? Just tell me idea. What is the idea behind this?
So in the case B, we are taking the scaling of the vector in the opposite direction.
That is fine, but I need eigenvalues and eigenvectors. You're right, it will be scaled by how much? How much it will be scaled? If suppose for matrix A it will be scaled by lambda, right? Then what will be scaled by for A inverse?
Lambda inverse.
M means 1 by lambda. Okay, so just okay, let's move. Suppose for matrix A I have eigenvalues lambda 1, lambda 2 and lambda 3, and for matrix A I can write Ax equal to lambda x, which means that this lambda is eigenvalue of matrix A. Okay, now I want to get what is the eigenvalues and eigenvector of A inverse. So what will I do is I will take A inverse on both sides.
Yes.
Okay, so you can see that this is nothing but identity matrix times x equal to lambda A inverse x. Okay, now let's move this lambda to this side. You will get A inverse x equal to 1 by lambda times I x, and that is A inverse x equal to 1 by lambda x. So what does it mean? It is another eigenvalue problem, that is bx equal to lambda dash x, where b equal to what? A inverse, and 1 by lambda is lambda dash, and eigenvectors are same. You can see that eigenvector has not been changed, which means that the eigenvalue of A inverse are nothing but for A inverse. For A inverse, lambda 1 dash, that will be nothing but 1 by lambda 1, and lambda 2 dash is what? 1 by lambda 2, and lambda 3 dash is equal to what? 1 by lambda 3. So this is the eigenvalues, and eigenvector will remain same.
So if the eigenvalues of the matrix A were lambda, then the eigenvalues of A inverse would be the inverse of the eigenvalues.
Reciprocal, don't say inverse, reciprocal. Okay,
Okay.
yeah, reciprocal is the more appropriate word. Okay, now let's talk about this. What is the eigenvalue of A, or A plus 2I? Okay, so tell me, Is there any idea for this? What will you do at this time? What will be eigenvalues? Just do things, right?
Sir,
Again, ax equal, I will start always. If I have eigenvalue a lambda and eigenvector x, then I will always start from this equation. Now subtract this 2i, not subtract, add 2ix both side. Okay, now you can see that it will become a plus 2i times x equal to lambda plus 2. You can see that here identity is also hidden. So lambda plus 2ix, again bx equal to what? Lambda dash x, which means that eigenvalue of b equal to a plus 2i will be what? Will be what? Lambda 1 plus
lambda 1 plus 2,
lambda 2 plus
2
2,
plus 2,
lambda 3
plus
plus 3. And what will be eigenvector?
it would be x only.
Yes, eigenvector will not change. Fine?
Sir,
Yes.
the third one would be lambda 3 plus 2.
Oh yeah, sorry. Fine. So, which means that, okay, I will do one more problem. Okay, after that I will generalize it.
Hello,
Fine.
sir.
Yeah.
Sir, how much time lecture will be going on?
I will finish today. Eigenvector, eigenvalue.
Sir, till what time, sir?
I don't know, but I will
Nine.
try to finish it.
Oh,
Okay, this
Okay,
is the
sir.
last lecture of the linear algebra. From the next lecture, I will try to start calculus.
Okay, sir. Okay, sir. Just I am asking because our recursive lecture is also going on from it.
Okay. If you want to join that. You can also watch from the YouTube video. Don't worry. Okay.
Okay, sir. Okay.
Yeah. Fine. Now the fourth question is, what is the eigenvalue and eigenvector of adjoint of A? Think about it. Use this idea. A times adjoint of A equal to what? A times adjoint of A equal to what? You guys are not following the previous lectures, which means that determinant of A times identity matrix, and this is also equal to adjoint of A into A. You can use either way, but definitely it will be equal to determinant of A times identity matrix. From that idea only I got A inverse, right? And A inverse is nothing but adjoint of A divided by determinant of A. This was the formula.
Yes.
Now use this equation to get the eigenvalue and eigenvector of adjoint of A matrix. Take 1 minute and just tell me what will be that. Use the previous idea, whatever I told you. Just use that. You will get it very easily. Did you get it? Shivani? What will be? Okay, first, from where should I start? Just tell me one first step. Very, very important step.
Ax equals to lambda x.
Ax equal to lambda ix, right? From where I have to
Yes.
start it? Now what?
Taking adjoint
Good.
of A.
Perfect. Adjoint of A times Ax equal to lambda is scalar, it will be outside. I can also take I, or it's not necessary, I will remove it. Adjoint of A times x. Now what?
This
Just
left
use
hand side
this.
would become determinant of A.
Yes, determinant of A times x equal to lambda adjoint of A x. Okay, now just swap this, so that will be adjoint of A x equal to determinant of A divided by lambda times x. So again it is a eigenvalue problem, that is by equal to lambda dash, sorry, b not y, it is just x, because eigenvector has not been changed. Okay, bx equal to lambda dash x, which mean that what are eigenvalues? Lambda 1 3 3 3, lambda 2 3 3 3, lambda 3 3 3 3. What will be lambda 1? Determinant of A
Determinant
divided
of
by lambda 1.
lambda 1.
Yes, that will be determinant of A lambda 2. That will be determinant of A lambda 3.
3.
Now simplify. You can simplify again. What is the determinant of A? What is determinant of A?
Lambda 1, lambda 2, lambda 3.
Perfect. Okay. Lambda 1, lambda 2, lambda 3 divided by lambda 2. Lambda 1, lambda 2, lambda 3 divided by lambda 3. So lambda 1 3 dash is lambda 2, lambda 3, lambda 1, lambda 2, sorry, lambda 1, lambda 3, and lambda 1, lambda 2. Fine. Is there any problem here?
No, sir.
I think you learned, right? All this.
Yes, sir.
Yes. Okay. Now let's move to another topic, diagonalization. Okay. Now, so from the definition, a square matrix A is said to be diagonalized if there exists an invertible matrix P such that P inverse A P is a diagonal matrix. What it is saying? it is saying that any matrix can be diagonalized if there exists an invertible matrix P such that if you multiply P inverse, pre-multiply A with P inverse and post-multiply with P, and that will result into a diagonal matrix D. So that then we can call as A as a diagonalized matrix, or this process is called what? Diagonalization. So which means that you can write, if P, there such matrix P exists, then you can write P inverse A times P equal to diagonal matrix D. So how it is happening? Tell me how it is happening. First, what will I do is, this is the equation, right? I can also write it as AP equal to PD. Is there any problem here?
No, sir.
Okay. So, from LHS, what is AP? AP is nothing but the matrix multiplication of A and P. Okay. For an example, I will take 3 by 3 matrix for simplification, for your understanding. Otherwise, you will not get it. Okay, can I write it like this? Just tell me whether it is correct or not. Think about it and tell me. Can I write it like this matrix multiplication?
Yes, sir.
Shivani? Kalpana is Kalpana here?
Yes,
Okay.
yes, sir, we can write.
Yes, perfect. Now, suppose there exists eigenvalue lambda 1 for corresponding this vector, and suppose lambda 2 eigenvalue exists for corresponding this vector, and lambda 3 exists for this vector. So can I write it like this? This one is ax, this one is a lambda 1, sorry, lambda 1x. This is nothing but what? A times p1, right? This one is what? A times p2. This one is what? A times p2. And that is nothing but A times p1 means what? Lambda times p1. This one is what? Lambda 2 times p2. This one is what? Lambda 3 times p3, right? Can you write it? Now after arranging, you will get nothing but what? Tell me. PD. This one is P1, this one is P2, this one is P3, and this one lambda 1 0 0, 0 lambda 2 0, 0 0 lambda 3. That is what? P times D. And what are those? Which means that P1, P2, P3 are what? When I can write eigenvectors. Fine. Which means that AP can be written as PD. Which means that when you pre-multiply P inverse AP equal to what? Diagonal matrix. And which means that P is what? Eigenvector matrix. And D is what? Diagonal matrix. Diagonal eigenmatrix, I will say. Diagonal eigenmatrix. There are numerous applications of this. Okay, so the thing is, what is the procedure then? What is the procedure to find P and D? So, what is the procedure? The first step is find n linearly independent. Why it should be linearly independent? Can someone tell me? Why it should be linearly independent?
Sir, what is n?
N linearly independent for n by n matrix I'm talking about. Okay, first I will complete it. First step to find P inverse and diagonal matrix. So the first you will do is find n linearly independent eigenvectors. Eigenvectors of A. And what are those? P1, P2, Pn. And second step, what will you do? Form the matrix P having P1, P2, Pn as its columns. Fine. And the third step is the matrix P inverse AP will be the diagonal matrix. Diagonal matrix with lambda 1, lambda 2, lambda n as its successive diagonal entries. First tell me why it should be linearly independent. Which means that what is the procedure? The procedure is, if you want to diagonalize the matrix A, then first you have to find eigenvectors of A. I mean, first you have to find eigenvalues of A, then eigenvectors of A. So after that, after forming the matrix P as all eigenvectors as a column of that matrix, and take inverse, then multiply A, then multiply P, then you will get as diagonal matrix. And what are those? Those diagonal matrix is nothing but lambda 1 0 0 0 lambda 2 0 0 0 lambda 3, that kind of thing. Now the question is, why it is required linearly independent? What if that you will get linearly dependent eigenvectors? Can we not form that diagonal matrix after that? Why it is required linearly independent? Think about it. It's a very important. That eigenvectors should be linearly independent, otherwise you cannot diagonalize. Why it is that? Are you getting what I'm trying to say? Kalpana?
Yes, sir.
And what if this matrix is linearly dependent, what will happen then? First think about it. The thing is, you have to find P inverse, and P inverse only one can be found when that matrix is non-singular, and that matrix will be non-singular only when
Linearly independent.
columns are linearly independent. Otherwise, determinant of that matrix will be 0. If these columns are dependent, which means that the rank of that matrix will be less than the order of the matrix, and which means that the determinant of the matrix will be 0, which means that you are not able to get P inverse. That's why it is needed that matrix or that eigenvector should be linearly independent. It's fine?
Yes.
Kalpana?
Yes.
Okay, let's take an example. Find a matrix P that diagonalize the matrix A 1 0 0 1 2 0 -3 5 and 2. So the characteristic equation will be what? Determinant of A minus lambda I will be 0, and after solving this you will get lambda minus 1 lambda 2 square equal to 0, which means that lambda 1 equal to 1, and lambda 2 comma 3 will be 2. You can see that it has repeated. Can you tell me, if eigenvalues are repeated, so which means that eigenvectors are linearly dependent? For corresponding lambda 1 equal to 1, you will get eigenvector. For corresponding 2 and 3, you will get eigenvectors. So the matrix P will be singular or non-singular?
It would be non-singular.
Non-singular. How?
Both the eigenvectors.
Which means that the matrix P will be invertible, right?
Yes.
Okay, you are correct. So what I'm trying to say is, if someone gets repeated eigenvalue, it does not mean that you can see that if eigenvalues are repeated, which means that you will get only one eigenvector, and for this you will get another eigenvector, and there is hidden eigenvector that is same for the corresponding lambda 3, which means that you will get P1 P2
Yeah,
and again P1. So is this matrix is singular or non-singular?
non-singular.
Non-singular. Just tell me, will this eigenvectors will be dependent or independent?
It would be independent. You can.
Okay, I think you are not understanding, but your answer is correct. Okay, let me explain. Here the thing is, here eigenvalues are repeating. Okay, so for lambda 1 equal to 1, so for lambda 1 equal to 1, so A minus lambda 1 I x equal to 0. So just take that. So that is 0 0 0 1 1 0 minus 3 5 1, and x1 x2 and x3 equal to 0 0 0. So for this eigenvalue you will get p1, you can solve it, 1 by 8 minus 1 by 8 and 1. This is the first column. Now for lambda 2 equal to 2, now the idea is you have only two different, distinct eigenvalue. So which means that you will only get two eigenvectors. But here there is a catch. For lambda 2, you will see that you will get independent two eigenvectors. For lambda 2 only. You don't have to get for different lambda because you don't have the different lambda for lambda 3, because here lambda 2 and lambda 3 are same. So for lambda 2 only you will get two eigenvectors. And what are those? Just substitute 2. Here you will get minus 1 0 0 1 0 0 minus 3 5 0 x1 x2 x3 0 0 0. Now add first and second row. So you will get 0 0 0 1 0 0 minus 3 5 0 x1. I will not do like this, otherwise I will not get echelon form. First I will multiply first row by minus 1. So 1 0 0 1 0 0, okay, minus 3 5 0 x1 x2 x3 0 0 0. Now R2 change to R2 minus R1. 1 0 0 0 0 0 minus 3 5 0 okay. Now I will change R3 change to R3 plus 3 R1. 1 0 0 0 0 0 0, okay, 5 0 x1 x2 and x3. How many pivots?
1.
1 2.
Yes.
When you do row reduced echelon form, it will move up. So you have two pivots,
Yes.
okay, and you have one free variables. So you can see that the first equation is x1 equal to 0. The second last equation, that will be x2 equal to 0, and x3 equal to what? You can take anything, right? Am I doing
Yes.
it wrong here? I think I am doing wrong here. No, fine. So that will be 0 0 and x3 equal to, you can take at t. So that will be v2 equal to 0 0 t. T you can take as a common, so 0 0 1. Now what is the P matrix? P1 is what? 1 by 8 minus 1 by 8 1. 1 by 8
Minus 1 by
minus 1 by 8 1.
1.
0 0 1, and again you can see that you are getting only one eigenvector, which means that you have repeated. Is it singular or is P inverse exists for this? So you can see that determinant of P equal to 0, because first, second column and third column are same, which means the determinant of P equal to 0, which means that P inverse doesn't exist, which means that what? A is non diagonalizable. Fine.
So for the repeated roots, we have two equal vectors, and
Yes. But what if, let's take a third example. Suppose you have 200, 002, sorry, 020, 002. What is eigenvalue? Lambda 1 equal to what? Lambda 2 equal to what? Lambda 3 equal to what?
2, 2, 2.
2, 2, 2. Right, fine.
Yes.
Okay, so you can see that 1 comma 2 comma 3 equal to 2. Now find ax equal to lambda x. You can see that 0 0 0 0 0 0 0 0 0 x1 x2 x3 equal to what? 0. How many free variables are here?
None.
3. Because there is no pivots.
Yes.
So which means that you have all three variables r, s and t, which means that x1 equal to r, x2 equal to s and x3 equal to t. So what is the v? R times 100
1, 0,
plus s times 0
0, 1,
10
0,
plus t times 0
0, 0, 1.
1. So what is the p matrix? That is 1 0 0 0 1 0 0 0 1. So you can see that this matrix is diagonalizable. P inverse exists. And why it happens? Because for the same eigenvalue you are getting 3 independent eigenvectors, and when you diagonalize it you will get P inverse AP equal to what? D. And what are those eigenvalues? 2. So you will get 2 0 0 0 2 0 0 0 2.
2.
Kalpana, it's fine. She is not here.
No.
I'm here.
Is it fine?
Yes, sir, but
Yeah.
it will take.
Yeah, tell me. Yeah, tell me. I'm listening.
I'm not able to catch the concepts because
Okay. Okay. Why? Where is the problem? Tell me. Just tell me. I will explain it. Tell me.
I'll have to rewatch the whole lecture.
Okay. Okay. Fine. Okay, fine. Now, let's move to the some important theorems. Okay, I will use this diagonalization thing to get how to get a raised to the power k. How you will get it? Okay, Kalpana, just remember this thing. P inverse AP equal to what? D,
D.
right? That's it?
Yes.
Okay. And what is P? P is a matrix where all columns are eigenvectors. Fine? Okay. Now the thing is, I want to get A raised to the power X matrix. How will I get it? So, So I know that P inverse AP raised to the power k equal to nothing but P inverse AP, P inverse AP dot 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 P inverse AP, and these are k times. Okay, and this is nothing but what? D raised to the power k. Fine, because you can see that if PAP equal to D and you are raising the power k, which means that it will become D raised to the power k. Now you can see that that is nothing but P times P inverse A, and this is P inverse P A times P inverse P A times P inverse P. So it will become A like that, and in the last it will be what? P, and that will nothing but D raised to the power k. So P inverse so P inverse A raised to the power k P equal to what? D inverse k. Now I want to get what is A raised to the power k. So you can see that just post multiply P both side, you will get P D raised to the power k, and post multiply P inverse, you will get P inverse. So if you have a matrix A and someone wants to get what is A raised to the power 100, then you have to get only eigenvectors and eigenvalues, and inverse of that you can easily get A raised to the power 100. Okay, let's take an example how I will get it. Suppose I have a matrix A equal to 0 0 1 2. Okay, now question is find A raised to the power 13. So what will I do? First I will write characteristic equation, right? So the characteristic equation, you will get determinant of A minus lambda I equal to 0. Okay, so that will be minus lambda 0 1 2 minus lambda equal to 0. That will be minus lambda times 2 minus lambda equal to 0. So which means that lambda equal to 0 and lambda equal to 2. Okay, now find eigenvector corresponding to lambda 1. So that will be 0 0. You can see that 0 minus 0, that will be 0 1 2 minus 0. Okay, so x1 x2 equal to 0 0. So from the last equation you will get x1 plus 2x2 equal to 0. So let x2 equal to s. So which means that x1 equal to what? Minus 2s. Okay, so the vector v1 equal to what? S times minus 1 comma 2. Okay, wait, yeah, minus 2 1. Fine, it's correct or not? Yes, it's correct. Okay,
Yes.
yeah, similarly find v2. So for v2 you will do minus 2 0, right, and 1 0. So y1 y2 equal to 0 0. Okay, so from here you will get minus 2 y1 equal to 0, and similarly the last equation will become 0 actually after the elementary row operation. So which means that if you take y2 equal to t, then y1 equal to 0. So vector v2 will be what? T times 0 and 1. So what is the P matrix? P matrix will be just arrange minus 2 1 and 0 1.
0
Okay, now find P inverse. P inverse is nothing but adjoint of A divided by determinant of A. And what is the adjoint? First element. For this corresponding, what is the cofactor? 1. Okay, for this it will be 1, but that will be minus times of n, right? So odd number, so minus 1. Okay, for this it will be 0, and for this it will be minus 2. And transpose, because it is a cofactor, I need adjoint, and adjoint is what? Transpose of that cofactor. And what is the determinant? Minus 2. Fine?
Yes.
Okay. So what you will get? You will get 1 minus 1, 0, 2 divided by minus 2. So you will get 1 minus 1 by 2, 0, 1 by 2, 1. Now you can find a raised to the power 13. How? Minus 1 by 2, 0, 1 by 2, 1. And what is the diagonal matrix? Whatever you get eigenvalues, just take that power. So 0 raised to the power 13. Okay, 0, 0, 2 raised to the
2
power
raised to the power 13.
13. And that is P. And P is what? Minus 2011. That's it. Just multiply it. You will get a raised to the power 13. It's a very easy multiplication. Not very difficult because many terms are 0. You know what? In my PhD Compre examination, they asked one question regarding the same concept. What is the value of e raised to the power a matrix if a is the same thing, same matrix, 0, 0, 1, 2? Just tell me what is the idea behind this. And it was 20 marks. It was 20 marks question.
Should we use the same equation ax is equals to?
No. How you will get e raised to e? You know e is exponential, right?
Yes, sir.
E raised to the matrix A, and this matrix is nothing but this. The same concept I have to use it. What is the e raised to the power A? That is nothing but identity matrix Taylor expansion. I plus A divided by 1 factorial, A square divided by 2 factorial, A cube divided by 3 factorial, plus 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 plus. Okay? Now you can see that at the place of I can write P inverse A raised to the power 0 P. At the place of A I can write what? P inverse A raised to the power 1 P, right? Can I write it or not?
Yes.
No, I have written inverse of that. Okay, so I have to write PD. Okay, yeah. I have to write P and D raised to the power 0 P inverse plus P D raised to the power 1 P inverse by 1 factorial plus P D square P inverse divided by 2 factorial plus, right? Now write it like this: D0 plus D by 1 factorial D square by 2 factorial dot 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 P inverse. Can I write it or not? And what is the D raised to the power 0? 1 0 0 0 1. And what is D divided by 1 factorial? That is nothing but lambda 1 raised to the power 1 0 0 lambda 2 raised to the power 1 divided by 1 factorial. Similarly, what can I write? Lambda 1 square 0 0 lambda 2 square. Are you getting what I am doing here?
We are applying the
Applying the same diagonalization theorem.
diagonalization on the of A on the diagonals of
Yes,
the
because I can write I can write this, right? For a equal to 1, a equal to 2, a equal to 3, that is nothing but p d raised to the power 1, d raised to the power 2, like that. And I did the
Yes.
same thing here. Now all these are second order matrix. So you can see that that is nothing but 1 plus lambda 1 after adding all this. Zero, zero, that is 1 plus lambda 2 by 1 factorial, lambda 2 square by 2 factorial, lambda 2 square by 3 factorial, and p inverse. And what is this? What is this? E raised to the power lambda 1, 0, 0, e raised to the power lambda 2, p inverse. Fine.
Yes.
And what is e lambda 1? That is 0. So it will be 1, 0, 0. And what is the lambda 2? 2. Just substitute p and p inverse. You will get e raised to the power matrix A. It was a very nice problem, right?
Yes.
Kalpana, are you getting it?
Sir, can you please explain the last third step?
This one.
Yes. This.
What is the expansion of e raised to the power x? 1 plus x
Plus x upon factorial 1 plus x square upon factorial 2.
right?
Yes.
It is happening like this only. For each corresponding elements, here actually divided by 2 factorial. Oh, I have already written 2 factorial.
So we have constructed the whole series into a big diagonal which is having the sum of.
Yes.
Okay, sir.
And it is nothing but the e raised to the power lambda 1, e raised to the power lambda 2. And you can see that lambda 1 is 0. So that will be 1. And what is the lambda 2? 2. So that is 2. Just take p and p transpose. Whatever I got it earlier. This was the p and this was the p and p inverse. Just substitute that. You will get e raised to the power a. Fine?
So it was like a prove that type of question that you have to
What?
evaluate.
I'm not getting what you are saying.
It was like evaluate this or
Evaluate,
like,
just evaluate, and I did that. They were very happy in my compre viva. Okay, yeah. So the condition of, okay, just tell me what is the orthogonal matrix. Before moving that, what is orthogonal matrix? Kalpana?
If transpose of a square matrix is equal to its inverse matrix.
Perfect. Okay, so which means that if Q inverse equal to Q transpose, then that matrix will be called what? Orthogonal matrix. Okay, so which means that Q inverse equal to Q inverse Q equal to Q transpose equal to Q transpose Q, all are identity matrix. That is called what? Orthogonal matrix. So there is a theorem here. The theorem is if A is n by n symmetric matrix, listen very carefully, symmetric matrix, okay, then then A is orthogonally diagonalizable. And A has orthonormal set of n eigenvectors. So which means that suppose if A equal to A transpose, okay, and after solving Ax equal to lambda x of this symmetric matrix, then that diagonalization is called orthogonal diagonalization, okay. And whatever you will get p1, p2, p3 as an eigenvector, those eigenvectors will be actually orthonormal set. What does it mean by orthonormal set? Which means that pi, if you take pi transpose with pj, and if this value is 1 if I equal to j, and if its value is 0 if I not equal to j, so this set is called what? Orthonormal set. Which means that suppose orthonormal set means what? Suppose you are getting this p1 eigenvalues, this p2 eigenvalue, and this p3 eigenvalue. So it is saying that if p1 transpose p2, p2 transpose p3, p3 transpose p1 equal to 0, and p1 transpose p1, p2 transpose p2, p3 transpose p3 equal to 1, then that set will be called as orthonormal set of eigenvectors. So that's why I have written index I and j. You can see that when I and j will be same, then that will be, when you take the transpose, that will be 1, and when both are different, then that will be 0. It is nothing but these two vectors are actually perpendicular to each other. These two, these two, these two. If these all mutually perpendicular, and if you take the dot product of this, or you can also say that the magnitude of p1 and magnitude of p2 and magnitude of p3, it is nothing but the magnitude, right? So if you take the magnitude and if it is 1, so that set will be called what? Orthonormal set. And you will always get orthonormal set of eigenvectors when A is symmetric matrix. So this is the property. Fine? Tell me, it's fine here?
Sir, if
Yeah, tell me.
if P is a vector, if P1 is a vector, is P2 is a vector, then under what circumstance their dot product is 1?
Which circumstances? P1 and dot product with P1 and P2.
Yes, sir.
So if that is 0, then that is not orthonormal set.
If they're okay, sir.
Okay? But if matrix A is symmetric,
Yes.
then those eigenvector set will be always orthonormal. And also if you rename it as a Q, then you will get Q transpose is actually identity matrix, and also Q transpose Q is a identity matrix. You can see that. Just take P1, P2, P3 and take transpose, that column will become row, right? So the multiplication is nothing but the this row with this column, and if this entry is 1 and you can see that you are multiplying this row with this column, that will be 0, and multiplying with this row with this column, that will be 0. Similarly 0, and with this that will be 1. So that's why you are getting identity matrix. Fine?
Yes.
Yes. So that set will be called as what? Orthonormal set, and that matrix will be orthogonal matrix. And you will always get orthogonal matrix when matrix is symmetric. Fine?
Yes.
Okay. Now next theorem. If A is a real symmetric matrix, then first property, the eigenvalues of A are all real numbers. GATE has asked this property many times. Eigenvectors are what? I just told you. Eigenvectors are orthogonal.
Orthogonal.
Okay? So the first property is, if the matrix is real symmetric matrix, I mean all entries are real and it is symmetric. Okay? Then all eigenvalues belongs to always real number. Okay? Let's prove this. How it is happening. Okay? So I know that I can write Ax equal to lambda x. Okay? Now let's conjugate. Suppose complex eigenvalue exists. Okay? So let's take complex. What do you say? If you take like this bar, complex conjugate, right? If you remember. Okay, so since this complex conjugate will be distributed in both matrix. Okay, now you can see that since all entries of A are real, so which means that there are no such complex numbers, so which means that the complex conjugate of A bar will be nothing but equal to A, and that is x bar lambda bar x. Okay, now take transpose. First step is what? Take complex conjugate. Second step is what? Take transpose both sides. So we'll get A x bar transpose equal to lambda bar x bar transpose, and that will be x bar transpose A transpose equal to lambda bar, that is scalar, so it will not be effect on this. This will be x transpose. Tell me.
In the last third step, we remove the bar from the A because it has real.
Because all entries are real I am saying that for every real symmetric matrix, all eigenvalues are real numbers. That is a theorem. So if we have taken the complex conjugate of A, since you can see that if 2 plus 3i, if you take the conjugate, it will become 2 minus 3i. Okay, but if you take the complex conjugate on real number, it will remain same.
Yes.
Okay, so if every elements are real, which means that A bar will be equal to what? A, right? Now take transpose. So it will become X bar transpose A transpose. Now I know that A transpose equal to what? A, because that is symmetric. Now multiply with X bar both sides. So it will become lambda X equal to lambda bar X transpose. Move this side. You will get lambda minus lambda bar times X conjugate transpose X equal to, sorry, yeah, here also equal to 0. Okay, can you tell me what will be the value of X transpose X? Will it be always greater than 0? You can check it. It will be always greater than 0, which means that this quantity can never be 0 to equate to 0, which means that what? You are reached only one conclusion, that is lambda minus lambda bar equal to 0, and it will happen only when lambda is real. Fine?
Yes.
Kalpana?
Yes.
Okay, now let's take second proof quickly. Ax. What was the second statement? All eigenvectors are orthogonal. Okay, so let's take one eigenvector. So that is corresponding to eigenvalues are lambda 1 x1. Okay, now multiply with both sides, or you can also take transpose both sides. So that will be x1 A transpose. Okay, x1 transpose A transpose equal to lambda 1 x transpose. Okay, now take x2.
Sir,
Yeah,
there would be transpose for lambda.
lambda is a scalar,
Okay.
and you cannot take transpose of a scalar quantity. That will remain same, right? That will be out of the matrix. Okay, and in this step, what is A transpose equal to A? So that's why I have written A transpose equal to A. That will be lambda 1 x1 transpose. Now multiply both side with x2. Fine. You can see that I can write ax2 as a lambda 2x2. Fine. Now bring both sides. Okay, I have written, yeah, it should be lambda 1. Lambda 1, lambda 1. Fine. Yeah, so you can see that will be lambda 1 minus lambda 2 times x1 transpose x2 equal to 0. Since lambda 1 is not equal to lambda 2. So what does it mean? Which means that x1 transpose x2 equal to 0, which means x1 is perpendicular to x2. Fine?
Yes.
I'm going very fast, right? I know that. It's okay?
Yes.
I will just take 5 minutes more and that's it. Okay, now let's take another thing. I know that what is the characteristic equation? P lambda equal to 0, and what are those? Minus lambda n plus lambda n minus 1 c1 minus lambda n minus 2 c2 plus cn equal to 0. Okay, now multiply both equation with x. I will take c1 as, because this is a constant, so I will take here c1 lambda n minus 1 x. Similarly c2 lambda n minus 2 x plus cn x equal to 0. Here you can see that I can write lambda n minus 1 lambda x. Similarly c1 lambda n minus 2 lambda x. Similarly c2 lambda n minus 3 lambda x dot dot dot. Just leave it cn x equal to 0. You can see that I can write at the place of lambda x as ax. Similarly c1 lambda n minus 2 ax. Similarly c2 lambda n minus 3 ax dot 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 cn x equal to 0. Now take every lambda outside, I mean inside here, because since it is a scalar, so you can get that it is nothing but a raised to the power n x plus c1 a raised to the power n minus 1 x minus c2 a raised to the power n minus 2 x dot dot dot. Here what is cn x equal to 0. So I can write minus an plus c1 a n minus 1 plus c2 a n minus 2 plus cn x equal to 0. Since I know that x is what? Eigen vectors, and it is not trivial, which means that x cannot be equal to 0. So what does it mean? You will get minus an plus c1 a n minus 1 plus c2 a n minus 2 cn equal to 0, and this is called Cayley-Hamilton theorem. You can see that I can directly write whatever you are getting characteristic equation, and at that place of lambda just replace it with a, and here I have to write identity matrix because it should be a matrix. Okay, so that's why you have to write it identity matrix. So you have to just replace lambda with a, and that equation will be called what? Cayley-Hamilton theorem. Fine?
Easy, sir.
Okay, one last theorem. If A is skew symmetric matrix, skew symmetric matrix, then eigenvalues are either 0 or purely imaginary. Okay, which means that if A transpose equal to minus A, then lambda belongs to either 0 or part of complex number, purely imaginary. I cannot say write it as a complex number, 0 or purely imaginary. Purely imaginary means what? 2i, 3i, like that. No real part. That is called purely imaginary.